Studied every day? Every day, every hour? Actually, it was nice to have a break. I think this lecture may be really long because I had like 2 extra weeks to prepare, so I just kept throwing in extra stuff. I wasn't rushed, so see how it goes. Anyone go anywhere interesting? Off the island? Oh, exotic Sydney? How was it after you got over the jet lag? What happened at midnight? Oh, I thought something turned back into a pumpkin or something. In Canada, the tradition is to fly to Cuba. Yeah, because it's cheap. Because the Americans can't go there. Yeah, recently. I don't know if that's, so we're all like, damn. Well, they had a national vendetta. National, what's it called? But yeah, they have a trade embargo on them, or with them. Are they really? Too fast, too Castro? No, but you could fly down there for $600. It was the flight to Cuba, a week at a hotel with food and booze. Be surprised how cheap things can get when you're in the States or in America in general. You have to be there to do it. It's not too bad. So the department bought me this new iPad Pro because I can write on it, but there doesn't seem to be a place to plug it in. So maybe next week I'll have that figured out. Do you like the slides better, or do you like it better if I write? You like writing? Because I can go through a lot more if I don't write. So if I start writing, I'll probably do only be able to do about half the number of examples. It's easier if you watch me. Well, I have it like this though, right? I usually do it line by line. So the bonus here is that this leads, well, it supposedly should lead to less mistakes, right? Because I'm not doing it on the fly, but the benefit is that I can do much more. The writing? Yeah, it is captured on echo when I write, it seems. It would certainly be captured on echo if I could do this. So my sister teaches, and she, instead of doing the answer, yeah, she'll just have the answer and then blank space and write into the PDF. So I don't have to switch back and forth. But anyways, oh, okay, but stop me. Ask questions. Yeah, it's this weird balance. Okay, so I have one vote for writing. Who else votes for writing? 2, 3, 4, 5, 6, 7, 8. All right, maybe next week we'll switch to writing. But I warn you, it's going to cut the number of examples I can cover, and at least in half. Huh? Well, I assumed everyone else who didn't vote for writing is voting for not writing. No absentees here. Oh boy. Okay. So let's continue. So this week we're going to cover a very important theorem called Greens Theorem. Greens Theorem allows us to relate the area of a given region to the length of its boundary. So it's a very elegant type of relationship. So specifically, Greens Theorem gives the relationship between a line integral around a simple closed orientable curve C and its double integral over the planar region D bounded by C. Greens theorem should be regarded as the counterpart of the fundamental theorem of calculus for double integrals, right? So that last sentence basically says this is an important theorem. It should be qualified as important as the fundamental theorem of calculus. So do you guys know anything about closed or oriented curves? No? Okay, it's very easy. This is a simple curve, and it's not closed. Right? It's because the endpoints are at different places. This curve is not simple and not closed because it has this crossover point here. The trouble with these crossover points is, well, if I want the tangent here, how many tangent lines are there here? 1. How many tangent lines are here? 2. Right? So the fact that there are 2 tangent lines here sort of messes with things a little bit, right? Because here an approximation of that curve is a line, and here the approximation of the curve is an x, and that messes with things a little bit. So we just pretend that we don't even have that case. Right? So this is a not simple, not closed curve. This is a simple and closed curve. Right? So these are the curves that we're going to be interested in particular, because they're going to be the boundary of some given area. Right? So the boundary needs to be closed, and the boundary shouldn't cross over itself. Although in the case when we have not simple and closed regions, we're going to be able to say that these are 2 regions, D1 and D2. But generally, we're going to be more concerned with simple and closed regions. We're concerned with boundaries that are simple and closed. Okay, so do you remember how curves could be oriented? We discussed this a little bit in lecture 1. Since C, the curve is parameterized by t, as t increases, this is going to represent a movement, right, along the curve. The orientation is going to be important. So when we are traversing the curve in a counterclockwise fashion, we're going to call this positive orientation. It's sort of backwards, I know. And if we're traversing the curve clockwise, we're going to call this negative orientation. Right? So just remember that the positive orientation, the orientation that we're normally going to desire, is counterclockwise motion along the curve. Okay, so here's the precise statement of Greens theorem, and we're going to go into it a lot in more detail. So if we let C be a positively oriented, right, counterclockwise traversed, piecewise smooth, that is, C can be defined by several curves, and as long as each of those curves are simple and connected at the ends, we can have a boundary which is actually the union of several line segments. And if P and Q have continuous partial derivatives on an open region that contains D, then the line integral over P dx plus Q dy is equal to the double integral over the region D, partial Q partial x minus partial P partial y dA. That may make no sense at this point, but notice, this already says that there is a relationship between the area that's bounded by D and the curve that is its boundary. Okay? Also recall that when we say PQ are the individual components of a vector function f. And so we wrote this, but we also can write something like this: the line integral over the vector function f dot dr. Here's some notation. When C is positively oriented, counterclockwise, and closed, we write this integral with a circle here. Right, so when I was in school, I always loved getting new notation, right? Because you can show your friends your homework and you'll look like a genius, right? Because we're using these very sophisticated looking notation. But all this means is that we're doing a line integral over a curve which is closed and simple. Right? And the reason that we come up with this extra notation is because there are extra tricks that one can play when integrating or line integrating over a closed simple region. So this is just a reminder. But it's cool. I thought it was cool when I was writing it. More notation: when D is the boundary, when D is bounded by the positively oriented closed curve C, Then we use the partial operator to say that the boundary of D is equal to C. So you can read partial D here as the boundary of D. Too often we sort of skip over the actual mathematicians who developed these things. These are real people who existed in history. They're normally crazy. Often they have depressing lives, and George Green was one of them. He started teaching himself mathematics from library books at the age of 9. And in 1828, he published 100 copies of an essay which he called On the Application of Mathematical Analysis to the Theories of Electricity and Magnetism. He was really one of the first people to try to come up with a mathematical representation for electricity. In 1846, I think at the age of around 30, he was admitted to Cambridge, and he promptly died a few years later, right, before anyone had noticed that he had produced anything of worth. Later, Lord Kelvin, as in the temperature Kelvin, located a copy of this essay, realized its importance, and had it reprinted. Right? And now, a couple hundred years later, I'm sitting here teaching you Greens Theorem. Right? So what a poor soul didn't realize the impact on mathematics that he would have before dying. But so is life. We're going to talk about proving Greens Theorem, but with a caveat that we're not actually going to be able to prove it in its full form, in its ultimate form, if you will. We're going to be able to prove it on if we make some assumptions about the types of regions that we're bounding. But even so, I'm going to be giving you some very hand-wavy proofs here. And because honestly, this isn't testable in any way. I just want to give those who are actually interested in the maths aspect of this a little bit of a peek. So if you don't want to pay attention for a little bit, that's fine. I've backloaded this lecture with tons of examples. Right? So I'll finish the lecture, and then we'll do a lot of examples. By the way, we just submitted your exam. So now you can be as horrible to us as you wish, because we can't make it any harder. I think 90% of the questions that I put on the exam are all integration questions. There's nothing on physics. Like there's no questions on work or like potential or anything like that. You have to become very proficient at taking integrals. And there's one question on a tangent plane and one question on a tangent line, but everything else is an integral question. In particular, one of the long answer questions is use Greens Theorem to answer this. So there's 1/4 of the long answer questions that I told you what the question will be. Right? So be sure to understand how to use Greens Theorem. Okay, so continuing. We're going to prove Greens Theorem for what we call a simple region. And a simple region is a region that is both type 1 and type 2. Do you remember these type 1 and type 2 regions that we have? A type 1 region means that we know exactly what the bounds on y is, and the bounds on x can be variable. And type 2 is everything but rotated a bit. So to prove Greens Theorem, so this is Green Theorem. I should have put a circle here. To prove Greens Theorem, it suffices to show, if we split this up into two pieces, that the integral over the closed curve C of p dx is equal to the double integral d over minus dp dy, or partial p partial y, and the integral of q dy, this part, is equal to the first half here. Right? We're just splitting the integrals into two pieces and matching them. Right? So our goal is to prove this and to prove this, and if we can do that, at least for the assumptions that we've laid down, we have proved Greens Theorem. Which one's wrong? Yes, I see. Yeah, this should be dq dx. Thank you. See, if I had my iPad, I could cross it out. But yes, good observation. Okay, so lemma. Lemma is a sub-result towards a larger result, so if its use here is appropriate. Let's show that the closed line integral over C of p dx is equal to the minus of the double integral over the region D of partial p partial y, BA. Proof. assume that D is type 1, right? Which means D looks like this, right? The X range is fixed between A and B, and the Y range is given by two functions, G1 and G2. Right? So you'll take an X in here, and then this will give you your bounds on the Y. Thereby, the double integral over D, partial P, partial Y dA, we convert this, right, using the rectangular region, well, semi-rectangular. Again, we're just employing the same methods we use for doing double integrals. So the double integral over this region D is, by definition, the integral from A to B, dx, the integral from G1x to G2x, partial P, partial Y, xy. And doing the inner integral first, we get, so what happens when we integrate partial P, partial Y with respect to Y? Well, we just get P back. And then we have to evaluate P, top minus bottom, which gives us this. Yeah, picture's maybe out of place. Well, let's continue. So we're taking an integral through here, and I'm going to continue expanding this out. But I think I wanted to sort of point out that we can break, if we can break any type 1 region into 4 pieces. Right, so can everyone see that this is type 1? Right, we go from A to B, and we move from G1 to G2. So if this is our region, then we can break it up into 4 pieces. C1 is the bottom part, C2 on the right, C3 above, and C4 on the left. Right? And we have to make sure that the orientation is counterclockwise. That means I can take this integral over P dx and break it up into 4 pieces. Right? A closed integral over the first curve, second curve, third curve, fourth curve. And this C3 is special, and I'll show you why soon. Okay, so notice that the change in x for C2 and C4 is 0. Right? If we're on this line here or this line here, x is fixed. There is no change in x. This means that we can eliminate this integral and this integral, right? Because they're both 0. Continuing, this is why I highlighted it, because of the bounds. Notice that this is the integral from A to B, but this is the integral from B to A. Why did I do that? Well, we have to ensure that we have this counterclockwise motion. So C3 actually starts at B and ends at A, which is fine because we know how to switch that. So I can take this integral which goes from B to A, and I can make it an integral which goes from A to B, right? Provided that I just put a minus in front of here. Continuing, we can group the integrand into one, right? This is a dx and this is a dx, and the integral is over the same region. So I can pull this out. We get the closed integral from A to B. Actually, this is no longer closed, of this. Going one further, we have shown that this is in fact equal to this. And so I should have numbered these equations, but I've shown that this double integral over D is equal to this, and in fact this is this expression here. So thus I've shown that the closed integral over Cp dx is equal, well, I proved the lemma. I proved that this is equal to that. So analogously, we can do the same thing for Q and develop the same equation. And if you combine everything there, then Greens follows. Okay, so who cares about that? What we're really interested in is that you're able to use this practically. So if we let C be the triangular region comprised of the line segments 0, 0 through 1, 0, 1, 0 through 0, 1, and 0, 1 through 0, 0, what is the line integral of x to the power of 4 dx plus xy dy? Okay, so the first thing we need to do is determine our region. Here it is. And we have to be very careful that when we parameterize this region, that the way that we do it is counterclockwise. If you don't do it counterclockwise, you're going to have a sign error. Right? So it's not that much of a disaster, but If you're finding things aren't working, check your orientations for signs. Okay, so note we could evaluate this integral via 3 line integrals. We could do a line integral here, here, and here. But instead, we're going to be able to convert 3 line integrals into a single double integral. Right? So C's orientation is counterclockwise, provided that we orient it like that. We also have f, our vector function, is equal to x4, x to the power of 4 xy. Right? We pull it from here and from here. This is p, this is q. And therefore, the partial derivative of q with respect to x is y. That, when we take the derivative of this with respect to x, the x disappears. And the derivative of p with respect to x, I don't know what this is, the derivative of p with respect to x is what? 4x cubed. Okay, so I'm going to convert this into a double integral using Greens. Right? So here we're going to apply Greens theorem. So this becomes y minus 0 because here I put y, and here I put 4x cubed. Oh, no. Sorry, this is dp with respect to y. So that means x to the power of 4 is 0. And so that's where this 0 comes from. Then I have to replace this dy and dx. Sorry, that was silly. Now we just can take this integral as we do normally. Right, so the integral from 0 through 1 minus x of y dy, well, y becomes y squared over 2. We need to take that from 0 to 1 minus x. That gives us 1/2 the integral from 0 to 1, 1 minus x squared dx. The integral of 1 minus x squared dx is 1 minus x cubed minus 1/6 from 0 to 1, which gives us a 1/6. Right? So instead of doing 3 line integrals, we did 1 double integral over a region. Okay, let's do another one. This is just another way of writing the same thing, right? Instead of giving you p dx, q dy, I'm going to give you a vector here, dot product, this vector here. Right? We'll have the same thing. So I want to integrate this over the closed circle, x squared plus y squared equals 9. Okay, so note that we know exactly how to parameterize circles, right? Using polar. Is this representation positive or negatively oriented? How could we test it? How can we figure it out? When I say positively oriented, right, this is a circle, right? And I've been using the words counterclockwise and clockwise. So this most appropriately, we're looking at a circle. It's a clock, basically. So how can we test if we're moving counterclockwise along this clock? Yeah, you can check two values along the curve, just 2, and see. So what's CT at 0? What's 2 cos 0? Cos of 0 is 1. 2 times 1 is 2. Okay. What's 2 sine of 0? 0. Okay, so our first point, our point at t equals 0, is 2, 0. Right? So that's the point lying on the x-axis at 2. Right? So 3 o'clock would be where that point is. Okay, so let's check t at 90 degrees, at pi half. What's 2 cos pi half? Cos of pi half, 0. Sine of pi half, 1. So 2 times 1 is 1. Okay, so our second point of pi half is 0, 2, which is midnight, 12 o'clock. Right, so at t equals 0, we're at 3, and at t equals pi half, we're at 12 o'clock. We're moving counterclockwise or clockwise through this curve? Counterclockwise, right? To move from 3 o'clock to 12 o'clock, That's counterclockwise movement. Right? I'm oriented towards you. Oh yeah, those two should be 3s. That would be parameterizing a circle of radius 2. All right, so just put a little tick here, and I put a little tick here. Hopefully I didn't propagate that error through the whole thing. Okay, so let's start out. I want to utilize Greens Theorem here. So this is P and this is Q. So the one thing you're going to have to remember is you're going to have to switch Q and P and put the negation in the middle. And so we need to take the partial derivative of Q with respect to X and subtract the partial derivative of P with respect to Y. So this sort of looks like a mess to begin with. So since we're integrating over a circular region, it's smart to convert to polar. So let's do that. What's our region D in polar? Okay, so the boundary is the circle of radius 3. So what then is the region bounded by that curve? Yep. The R, the radius of our circle, can be anywhere between 0 and 3, and the angle we're permitted are all of them. Right, so that gets us everything within the circle. All right, so that's how I can convert to here. We're going to go from 0 to 3 on R and 0 to 2 pi on theta. Here's our R from the Jacobian. Now, how else did this get eliminated? So if I take the partial derivative of this with respect to X, what's left? Well, 7. And so 7 in polar is 7. If I take this with respect to Y, what do I get? Well, 3. And 3 in polar is 3. So what we're left is this integral, which should be easy to do. I'm going to rearrange it like this because it sort of makes it more makes the integrals more easy. Did I ever mention this? So if you, or did your past professors mention this? If you're taking the integral over 1, what's a quick way of determining the integral? So when you take an integral like this, it's always going to be the top minus the top thing minus the bottom thing. Right? So for the rest of the lecture, when we have simple integrals like this, I'm just going to write this difference. Right? I'm putting this 0 here on purpose, right? To demonstrate that this 0 is the 0 down here. Anyways, to evaluate this, we have 4 times this integral, which is 2 pi minus 0, times this integral. So this is going to be r squared half from 3 to 0. So we're going to have 3 squared half minus 0. And in the end, that gives us 4, 8 times, okay, so 2 cancels with this 2. So we have 4 pi times 9, 36 pi. Right, just to go back a bit, we're just utilizing this. Oh, this. Ignore everything else today. That this is the most important thing right here. Okay, there are a couple of corollaries from Greens theorem, and a corollary is sort of a result that's important that follows almost immediately from another theorem. So if we know that P of xy and Q of xy is 0, right? That is everywhere on the curve that C is, if P and Q is 0 on that, then we can very easily evaluate this double integral. So consider that you're given a double integral like this, which may look complicated. If it is the case that you can divide the integrand into pieces like this, so that P and Q satisfy this property, then you can make the integral 0 very easily. Right? This may have been super sophisticated or required a lot of work to evaluate, whereas this is pretty easy, right? So if you're working with an integral over a region, it's very difficult. This corollary may help you. A more important corollary is if D is a region, so that its boundary is closed and simple, then the area of D is given by these equations. So it's either the closed line integral over the boundary of dx dy, or it's minus the closed line integral over the boundary of dy dx, or 1/2 the closed line integral around the boundary of dx dy minus y dx. So let's give this a proof. I'm going to prove this last one here. So recall the area of D, right, is given by the double integral over D of 1 dA. Thus, if we choose a Q and P so that the partial derivative of Q with x minus the partial derivative of P with y is 1, this means that the double integral over the region d1 dA is equal to this via Greens Theorem, is equal to the closed line integral around the boundary of d p dx plus q dy. And then what are our options for p and q? We need to pick p and q so that this equation is held. Well, there's at least 3 options. If p is 0 and q is x, then certainly dq partial q partial x minus partial p partial y is 1, right? Because dq dx is 1. This also satisfies this equation. dp by dy is minus 1, so minus minus 1 is 1. Right? And it's also true if we choose p and q like this. They're certainly not the only options, but these are the 3 sort of most clear options. And if we move back to here and plug in our values of p and q, then this follows. So here's a practical question. If I tell you that your boundary is enclosed by the equation that gives an ellipse, what is the area enclosed by an ellipse? Right? Does anyone know the equation for the area of an ellipses? No, I don't think you should. It's not that simple. Okay, so there is a parameterization for the ellipse. It's given by a cos t, b sine t, for t from 0 to 2 pi. You should verify that C is closed and positively oriented. Right? You can verify that it's closed by checking that its value at 0 is equal to its value at 2 pi. And you can determine if it's positively oriented by just checking 2 consecutive values of t, right, as we did with the clock example. So using the previous corollary we have, the area of the ellipse is equal to 1/2 the closed line integral x dy minus y dx. Well, in this case, our x is a cos t, our y is b sine t, and dy, I didn't write it down. Okay, so if y is b sine t, then dy is b cos t dt. Yes? I wish I could write on this now. Let's switch to the visualizer. Okay, what do we have? We had x is equal to a cos t. Right? This means that dx by dt is equal to a sine t. Yes? Minus. Which means dx is equal to minus a sine t dt. Similarly, if we have y is equal to b sine t, this means that dy is equal to b cos t dt. Make sense? Because we're going to have to do this 100 times today. Maybe I'll just leave that up. Okay. So I substituted x for this. I substituted dy for what I wrote on the visualizer. I substituted b sine t for this y, and dx for what I put up on the visualizer. And after doing that, we have this equation here. And if we simplify a bit, we get ab cos squared t plus ab sine squared t, dt. And what does the inside now evaluate to? AB, right? Cos squared t plus sine squared t is 1. Right, so we have AB over 2, integral from 0 to 2 pi dt, which means that the answer is pi AB. Isn't that neat? Right? the area of an ellipse of this form is pi AB. That's proved. Something even cooler is the fact that this Greens theorem gives us a method for practically computing the area of a region with a tool called, I've been practicing this, but I'm not going to be able to say it correctly. Yeah, planimeter, planimeter. That's definitely not how you say it, but this is how the tool looks like. So this is something that always puzzled me when I was younger, right? We're taught in class, here's a rectangle and here's how we compute its area. Here's a circle and here's how we compute its area. But we were only ever shown how to compute areas of things that had straight lines. I guess a circle is a rectangular region in polar. That's why it was easy to come up with that equation. But what does Greens theorem tells us? Well, it says if we can traverse a curve and at each point of the curve count the dx dy contribution, then we know that summation has a relationship with the area of the inside region, right? Again, the boundary of a region is related by Greens theorem to the area. Right? So what you would do is you would take this machine here, right? And these wheels move as you move this tracer arm around. And as you move the tracer arm around, it sort of increments the contributions. Right? And then after doing some computations, it gives you the area of the inside. Right? So we can take areas of irregular shapes, which is pretty cool. Right? Biologists were using this. They would use it to trace around leaves and things like this, cells. Cartographers use these tools in order to estimate the area of a country. Right? You could make this if you. I Googled this a little bit, and there's a lot of YouTube videos of people going and making such a tool. Right? So here's an example for you engineers of actually how maybe these sort of weird, flighty theorems can actually be used to develop tools, like physical tools in the real world. And this picture is finally one I didn't bother drawing. I stole this from Stuart's book. Okay, so here's some more theorem that's not really necessary for you to understand for your exam, but you should still be aware. So we proved Greens theorem for simple regions. Right? Regions that could be described both as type 1 and type 2. We can extend that a little bit because we can take regions like the one below and cut them. Right? Cut them so that a region which was not simple becomes simple when you cut it like this. Right? So if you look here at this cut line, we have to be careful about how we move along it. Right? We always need to have a counterclockwise simple closed curve. Right? So if I want to cut this here, right, the whole thing, the boundary here, of course, is closed and simple. But if I want to cut it here, I have to make sure that at this cut, I move this way down the line. Right? That's the movement. And on this side, I have to make sure that I move up along that curve. Right? And the fact that those orientations are opposite is crucial. Because when we work out the proof, the contributions, the line integral along C3 in this direction is exactly the opposite of the line integral over C3 in this direction. Right? So all of those contributions are going to cancel. We're going to arbitrarily divide up this region, but ultimately our division lines will not matter. Okay, so if we apply Greens theorem to the regions individually, D1, D2, so D1 is bounded by C1 union C3, and D2 is bounded by C2 union minus C3. Right? Using Greens theorem on each of these allows us to write this, and as I said, since the line integrals along C3 and minus 3 cancel, we have that the integral over the region enclosed by C1 and C2 is equal to the double integral over d partial q partial x minus partial p partial y dA. So nothing's changed here. It says, if you're given a region which doesn't comport with our earlier assumptions, you can cut it in half, and actually doing so doesn't really affect its usage, right? Because you could do these two line integrals independently by putting these C3s in here, but they're just going to cancel anyways. And so this is Green's theorem for the union of two regions in space with a boundary that's broken into two pieces. My friends laughed at me when I showed them this picture. I don't know why. So the same argument could be modified to establish Green's theorem for finite numbers of non-overlapping simple regions like this. Right, so we can take that result on two regions and extend it to finitely many regions. Right? If I can do it with two pieces, then I can do it with 3 and 4 and 5. And the more comprehensive proofs of Green's theorem basically say, give me your region, and we're going to cut this region up in such a way that the individual regions can be added, right? But when you do this, you just have to be careful about the orientations of these lines, right? We move down here, we move around, and then we move down. We move up through here and around through here. And again, all of the contributions on these cyan lines will cancel. Right, so you don't really need to understand that, but if you want to study the actual proof of Green's theorem, which is interesting if you're studying electromagnetism, this is the central idea, right? That they prove Green's theorem on a simple region, and then they can take more complicated regions and divide them into these simpler regions, and then exploit the fact that integrals add over these unions. Okay, so who cares about the theory? Well, maybe mathematicians, but certainly not the engineers. Let's evaluate the closed line integral over y squared dx plus 3xy dy, where C is the semi-annular, simply connected region D that's in the upper half plane between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Right? Or the region given by this picture. Right? So is it counterclockwise? Well, yes, because I put these arrows on. But generally, make sure to check. Because we're going to have to be careful here, right? Because normally when we parameterize circles, we have counterclockwise. But on this circle, we have to move clockwise. And so just keep this in mind when you're parameterizing, because you will screw up signs and things won't equal. So D itself may not be simple, but the y-axis divides it into two simple regions. Right? So if I cut this in half, did I draw a picture? No. Right, so this region is not both type 1 and type 2. If I cut it in half, the left-hand side is type 1 and type 2, and the right-hand side is type 1 and type 2. And since that's the case, the theorem that we just developed says we can just use Green's theorem as normal. So really, practically speaking, you can just convert this using Green's as normal. Right, so if D, what is the rectangular region given by D now? Now we just have to use our old methods of doing double integrals. Looking at this picture, you should be able to do it very quickly. Yeah, well, what are the possible radiuses that are allowed? Right, you have to imagine that you have a stick, right? And you're allowed to extend your stick by a certain amount and rotate it by a certain amount. So the stick can start at 1 and end at 2, and it can start at angle 0 and end at angle pi. Right, so in polar, our region dr theta is 1 through 2 times 0 through pi, and therefore Green's theorem says that the integral over the closed region C, y squared dx plus 3xy dy, is equal to, by Green's theorem, the double integral over the region D, given by this, partial derivative of q with respect to x, minus the partial derivative of p with respect to y. If we evaluate these partial integrals, this first one becomes 3y, and the second one becomes 2y. 3y minus 2y, is y, right? And then converting this to polar, y gets r sine theta. Here's the Jacobian r, dr d theta. And now we just integrate as normal. 14 thirds. Right? So here, right, be careful. It's going to be very rare that we'll give you a line integral. If you wanted to do this using classical methods, you would have to do 4 line integrals. 1, 2, 3, 4. And so just keep this in mind, because we may not say use Greens in order to evaluate this. When you see a closed line integral, ask yourself first if Greens applies, because it will save you a lot of time. Greens theorem for regions with holes. Greens theorem can be extended to apply to regions with holes. Right? Suppose that we have a region D1, which is in here, which is, oh no, we have a region D1 which is bounded by C1, and a region D2 which is bounded by C2. Then the region D is the set difference of those two sets. We also have to assume, and you'll see why, that C1 and C2 have opposite orientations, with the outer boundary having positive orientation. Right? So the outside needs to be like this, and the inside needs to be like this. And this next picture will show you why. Because we're going to need to divide this region into 2 regions that don't have holes. Right? And if we can divide them into 2 regions that don't have holes, then we can apply all the methods that we've been developing this whole time. So do you see that D prime and D double prime here are 2 regions without holes? And you also know that we are able to implement Greens theorem for those types of regions. Let's investigate why we insisted that the orientation of the outer boundary is opposite of the inner boundary. Well, because if we wanted to cut this like this, we have to make sure that the flow of the boundary is correct. So if I move around like this, then I move into here, and then I want to move from left to right. Right? If this was oriented backwards, I'd be stuck. I guess I could have moved underneath here, but then they wouldn't be non-overlapping regions. Right? So again, we move around here, we move through this, up around here. This one? Yeah, I should have inverted these. But like, okay, so we go down here and then up through here, and then right. Yeah, I'll invert to be consistent. These pictures took me all week to figure out how to draw. It's very hard to draw something which looks like a jelly bean. Okay, so extend the circle. What? In terms of the pictures? I don't want a disk, I want a jelly bean. Well, circles would be easy to integrate over. We already know how to integrate over circular regions, annular regions. Right? That's what we've been developing now. The whole purpose of Greens theorem is to be able to integrate over irregular regions, regions which aren't nice circles or squares. So although I could have put circles here, it totally would have missed the purpose of the lecture. Is that we really are able to do it for any sort of weird curve. Okay, so we're not, I doubt we'll ever actually give you any examples with these holes. It's just good to be aware that you can cut regions with holes out so that you can employ Greens theorem. So I don't think I'm actually, if you want to look into the notes, oh, do you guys know that I put notes online? You guys were asking for them? Okay, cool. I did a big pass on it over the break, so please re-download the notes. I've been doing a lot of corrections. And if you find mistakes in the notes, please email me. Right? The notes are going to be the version which has the least amount of mistakes. I'm not going to go back and fix the slides, but I will fix, I'm going to put my emphasis on fixing the notes rather than the slides. But if you send me mistakes, I'm going to talk to Bjorn to see if that can't be rewarded somehow. Like maybe we can give you some bonus marks for those of you who find mistakes, because it's very useful. Okay, so for those of you who want to see a proof of Greens for dividing this region into 2 pieces, you can take a look. It just utilizes the same type of cancellation, but I get the impression that it's not that interesting. It's just note that, again, if you take a line integral along this blue line in one direction and take a line integral along the blue line in the opposite direction, that those contributions are going to cancel. Right? So in the end, these things are going to be ignored. Right? It's great. We can divide these regions into pieces, and the contributions of the regions are 0, provided that we orient them properly. That clock is wrong, right? Okay, so we're going to finish by working through an assortment of exercises. Do you want me to switch to the visualizer then? Okay. Anyone have some paper? Oh, actually, maybe I can use the iPad. Let's see if this works. I'll see. All right, I'm going to use this again. Okay. Normally, when I'm typing it up, that's going to be a lot more organized. Let's try this. Is that visible? Is this light? Cool. Okay. Let's do this. So what is the question we're being asked? Evaluate the line integral over the closed region C of y squared x squared y dx dy for C is the rectangle. Okay. First thing we need to do is determine our boundary. Right, so we're going to do this both using the normal method and Greens method, right, just to confirm that they match. So what is our region? Well, if I do zero, 0, 5, 0, 5, 4, and what's this? It is 0, 4. Those are the endpoints, yeah? Cool. Okay, so we need to move around the region like this. Right? Counterclockwise. And it's going to bound our region D, right? So let's call the curves around here C0, C1, C2, C3. Okay. What is C0? How can we parameterize it? What's a parameterization for the straight line C0? This needs to be quick. 0? I don't think so. You need a parameter, right? Like t. B, 0, such that t goes from what? 0 to 5. Yeah. And will this move us from left to right? I think so, right? If t is moving from here to here, then our curve is moving along the same way. Okay. C1 is what? Need to parameterize C1. Said that. 0. And oh, this is wrong. It's not 0. What's true about everything here? Well, what's the x component on C1? Always 5. What should be the second component? T. And what are we taking it? Zero to 4. Perfect. Okay. I think cool stuff like this. Cool. Okay, what about C2? Whoops. Okay, let's do the easier one first. What's true about the y component for the entire 4? What's the first component? Maybe. For what t? For what range? Nope. That will give us this line. We could say positive t from 5 to 0, but that's atypical, right? We don't normally write that. You're almost there. 5 minus t. 5 minus t, such that t is in what? 0 through 5. Right, this means at 0 we're going to be at 5, and as t increases we're going to decrease. Right, so that means we're moving this way. But your suggestion of minus t4 is not right under the same region. Okay, finally, what's the last one? First component 0, the second component is, did it again. Not minus t. Minus t takes us into the bottom half. Huh? Oh, 4 minus t. For what values of t? Right? So this is going to take us from the top of the curve, and as t increases, we're going to be going down. Right? So we've taken care to set up our components so that we are moving counterclockwise around the region. This question took me like 6 times, because even I kept screwing up the orientation. Okay, so what do we have here? Our function f is y squared x squared y. Right, which is equal to our PQ. Okay, so let's take the closed integral over C naught of y squared x squared y by x dy. All right, so what's the first step here? If this is C naught, this means that our x and y is equal, oh god, that's going to be annoying. Our xy is equal to t0, which means that dx dy is equal to dt 0. Everyone follow? Oh, to get to yeah, well, oh, okay. That's a good idea. Okay, so does everyone get this? Right, on the curve C naught, we have x is t and y is 0. Right? So that means xy is t0 and dx dy is dt d0. Okay. That means this is equal to what? Well, integral 0 through 5. Y is 0. X is t. Y is 0. Dot dt 0, which is equal to what? 0. Okay. What curve do you want to do next? Okay. Well, I did one of them. I have the rest of them ready, so I'm going to do I'll do the rest now. I think maybe this is one I'm going to try to balance it like this. Oh, I did Greens first here. Okay, let's come back to Greens. Okay, here's the parameterization that we developed. So for C0, we determined that it was 0. For C1, we do the exact same thing. Right? On C1, we have that x and y is equal to 5t, which means that dx is 0, dy is dt. That means to do that line integral here, the first thing we're going to do is swap out these values for the ones in here. Right? So we take the line integral from 0 to 4, t squared, 5 squared t, d0 dt, which leaves us with 25's half t squared from 0 to 4, which is 200. So the contribution on C1 is 200. In the exact same, like this, we're just repeating the exact same thing over and over again. If you can get these line integral downs and the Greens down, that's 1/4 of the long answer questions that you can get perfect on the exam. There are 30 multiple choice questions. Yeah, again, so on C2, I think this is the most complicated one of the curves. We have that x is 5 minus t and y is 4, which means dx is minus dt and dy is 0. So putting those values into that integral, we get 0 to 5. The integral of 16 from 0 to 5 dt negated, which is equal to minus 80 of the contribution of C2. And C3 is just like C1. The whole contribution is going to be 0 here, right, for the same reason. So what did we discover? Well, if we combine our answers, right, the line integral over the 4 pieces combined, we can add them. Right? We had this result from the lecture before. That is, we know that the line integral that the integral of C0 union C1 of something dt is equal to the integral of C0 f dt plus the integral of C1 f dt. These integrals are additive, and so if we can add the integrals down here. So that's 120. Okay, so the next thing we want to do is do the same question using Greens theorem, and then confirm that we're getting the same answer. So let's go back. Okay. So let's look back at our region here. How can we describe D? Oh, much better. Right, so how do we give D as a region? Yeah, cool. Okay, so now, well, just let me take this with us. Okay, so we need now to employ Greens, which is what? The integral, closed integral over C of P, Q, dx, dy equal to the double integral
over d partial q partial x minus partial p partial y dA, where boundary of d here is equal to c. Okay, so what is our P and Q? Have this. Okay. So how do I continue here? It's going to be the double integral from 0 to 5, 0 to 4. dq dx is what? 2xy. dp dy is 2y. And the first thing is dx, dy. Okay? Inner integral is with respect to x, so we get x squared y minus 2xy, 0 to 5, which is what? That's 25y minus 10y, 0 to 4, y, which is equal to 25's halves, y squared minus 5y squared. Oh, I could have combined those two. Okay. So this is what? This is 15y. So this is equal to the integral from 0. This is equal to 15 halves y squared from 0 to 4, which is 16 halves times 15, which is 8 by 15, which is what? $120? Was that what we calculated? Yeah. Okay. So I'm probably not going to put those because this is better than this. You can always look at the echo. Well, I'll see what I can do. Apparently, though, the file size of these things is huge, right? Because it's images. It's not text. Yeah. No, because the PDF is just going to try to convert an image. What makes the PDF a PDF is the fact that it's characters. PDF, printable document format. It's just a way that we've all agreed that this is how you print a T if I tell you to print a T. It has nothing to do with images. I can make it a PDF. It's still going to be an enormous PDF. Right? Yeah. Okay. I have another one. Do you want it on the thing or here? Do it on there. You're the one who was campaigning for it. Okay, so let's evaluate this line integral and confirm that it matches with Greens. So in this case, we have a triangle, and again, the most difficult thing is going to be making sure that we're traversing this triangle in a counterclockwise way. Right, so you should be good at parameterizing lines. Right? So the thing on the bottom here is we want to go from 0, 0 to 1, 0. So that means it's a T in the first position, and a 0 in the last position. We run from 0 to 1. Right, so from here to here. We want to start at 1, 0 and end at 1, 2. That means we can take the, we can parameterize C1 by this vector. The first component is 1. The second component is T. And we take T from 0 to 2. So this line is sort of the harder one. But it's, you can just determine the actual equation for this line, the y equals mx plus b. Or you can think of it like this. So we know we have to start at 1, 2. And I have to subtract what? Well, the rise over run here is 2, and then the run is minus 1. And so that's what's in here. This is t times minus 1, 2. Right? That's saying start at this point and then move in this direction. I sort of built up, I developed a way of running a parameter through a 3D curve. But anyways, you can confirm that. So there's our boundary here. So let's do it with Greens first. So in the boundary of D is that triangle. We have that the region D takes x from 0 to 1 and takes y from 0 to 2x, right? So I can take an x value between here and here, and I can take y values that start at 0 and end at this line. And that line is 2x. So utilizing Greens theorem, we convert the line integral over the closed region, line integral over the closed curve into the double integral over the closed region. This is dq by dy, dx. This is dp by dy. If we work all of that out, we are left with these, right? So 2xy cubed and x. And then it's just routine doing the rest of these integrals. It's all there. We end up getting 2/3, right? So 2/3 is our target. Okay, now we have to do 3 line integrals and sum the results, and hopefully we're going to get 2/3. Right? So on C0, that's the line on the bottom. We have that x and y is equal to t and 0. This means that dx is equal to dt, and dy is equal to 0. And so substituting all of those values into here, we end up evaluating the integral from 0 to 1 of, well, it should be t times 0 dt plus t squared times 0 d0, which gives us 0 contribution. C1, that's the line that's going up and down. We do the exact same thing. Right? First, we write down x and y is 1 and t on C1, which means that dx dy is equal to 0 dt. You take all of these values and you substitute it into the integral down here to get xy, 1 times t, dx, 0, x squared is 1 squared, y cubed is t cubed dt, which is equal to the integral from 0 to 2 t cubed, and from there on it's standard, right? So the integral of t cubed is t to the 4th over 4. From 0 to 2, that's going to give us 16 over 4, which is 4. All right, so we have 0 and 4. On C2, that's the line that's going like this. Right? We have xy is equal to 1 minus t, 2 times 1 minus t. That means that dx is minus dt, right? dy is minus 2 dt. Right? So this is going to involve some trickery. Okay, so I'm going to take these values, I'm going to put them into here, and we get this out of it. I'm going to clean this up a bit. Right, so notice that I took the negation out, right, from this dt. But also that we have a 2 here, a 16 here, and everything else is 1 minus t. What's the next step here? Well, there are 2 things. The not smart way of doing this would be to expand. You could expand all of this into one polynomial and then integrate, but you would spend a lot of time expanding 1 to the t to the power of 5. And who knows, maybe I'll put 100 there for your exam. Right? But you had the correct answer, that is to do a substitution. Which substitution? U is equal to 1 minus t, which means du is equal to minus dt. Right? That's what happens if you take the derivative of the left-hand side and the right-hand side here. This means you go, all right, so if u is 1 minus t, that means u goes from 1 minus 0, which is 1, to 1 minus 1, which is 0. I replace this dt with a minus d. I replace dt with minus du, right, which gets rid of this negation here. And then I'm left with this integral. So what's the next thing I should do? Right? This sort of looks bizarre. Swap the bounds, right? Throw a negative in front. So now we have a negative 2, integral from 0 to 1, u squared plus 8u5, u to the power of 5, and this is fairly routine from here on in. In the end, we evaluate this as minus 10/3, and 0 plus 4 minus 10/3 is 2/3. So that's confirmed. What time is it? 6:24. This is another question of the exact same. Well, let's do it. Okay, so let's evaluate the line integral of y dx minus x dy, where c is the radius for a circle, centered at the origin, both directly and with Greens theorem. Directly won't. So in this case, it's anyone's game, right? Who cares if you want to take a line integral over the circle? That's one component, right? In this case, I'd sort of be more inclined to do a line integral over Greens theorem. Right? You can use Greens theorem provided that C, the line integral, is closed, counterclockwise, and never crosses over itself. So our curves are parameterized by a function. Well, let's do the circle example. Yeah. Well, so on a clock, right, if your hand is moving this way, we call that counterclockwise. And if it's moving this way, we call it clockwise, right? Okay, so, but note that we can parameterize this circle, and let's just assume that the radius is 1 by cos t sine t, right? And earlier on in this class, we discovered at t equals 0, our point is here, and at t equals pi halves, it was here. Right? Which means that we must have been moving from here to here. Right? So if you look back at the lectures we did on parameterizing curves, we talked about these curves really representing movements of particles through space. Right? So what I mean by counterclockwise, right, is you can explain it mathematically. It's just a little bit sophisticated. It's like, well, if you increase your t, then your x value has to be less than the x value that you were at before. But it's enough to just view this as counterclockwise. Just you test 2 or 3 points, and it'll give you an impression on how you're moving. But for circles, we always know that it's counterclockwise. So just keep that in your mind so you don't have to waste time on your exam. Okay, so with Greens theorem, right, because this is closed, we can evaluate this integral by instead doing a double integral. Right? So the region that's enclosed by the radius for circle, these should be routine by now, is the region that takes theta from 0 to 2 pi and the radius from 0 to 2. So this line integral given here can be converted to the double integral given by Greens. Right? So this is q. We take dq dx. This is p. We take dp dy, and we take the difference. So we're going to get minus, d minus x dx is minus 1, and dy by dy is 1, and minus that is minus 1. So we have the integral, double integral over minus 2 dA. I'm going to switch to polar in order to be able to put the bounds of the circle in. So there's our minus 2. There's our Jacobian r, dr d theta. We're going to take r from 0 to 2, theta from 0 to 2 pi. And again, now this is routine, right? When you get minus 8 pi. Directly, right? And as you see here, now the direct method is faster than using Greens theorem. Right? So it's just another tool in your toolbox. It's not this sort of, it's not a blunt instrument. Right? You still have to take some consideration when you're using these tools. But here we have x and y is equal to 2 cos theta and 2 sine theta, which means dx and dy is minus 2 sine theta d theta, 2 cos theta d theta. I did that on the visualizer a little bit before, which means if we utilize just the method for taking a line integral, that is taking all of these values and substituting into here, we end up getting this expression over here. I guess that 4 is not supposed to be there. And again, it's a fairly easy integral to take. Minus 4 from 0 to 2 pi of sine squared theta plus cos squared theta. D theta is just going to be 1. So this is minus 4 times 2 pi, which is minus 8. Does that match? Yeah, perfect. that one. There's just one difficult one that I wanted to do with you guys. Maybe this one was it. Okay, let's finish with this example. So if I asked you to evaluate the line integral over the closed curve C of y plus e to the root x dx plus 2x plus cos y squared dy, where C is the boundary of the region enclosed by the parabolas y equals x squared and x equals y squared. So let's draw that. So we have x squared, y equals x squared. This is x squared equals y. This point here is 0, 0. What's this point? 1, 1. Okay. So this is the region in question. I wrote y equals x squared and x squared equals y. This? Yeah, this is the parabola. Is this? Oh my God, yeah, sorry. Oh my God. In my head, I'm thinking, man, my kids are stupid. Oh no, that's going to be there for posterity, right? X is equal to y squared. Thank you. Yeah, so it's that region that we're interested in. So how can we represent our region D? Okay, x goes from 0 to 1. Gotta be careful here. What's on top? Right, we're gonna be drawing a line here, right? At some x. So what's this value and what's this value? So we're going to have root x to x squared. Well, this curve no. No, we're not. See, this is why I like using slides better. We're going to go from I think we're going to go from y here is root x, isn't it? And y here is x squared. So I think it's root x through x squared. All right, well, I did the slides too, so. Called it. What did I screw up here? Or did I screw up that? If x is here, then what y value is this? Oh God, yeah, sorry. I blame you. I blame you for bringing this pox upon my house. Okay, anyway, so we have that semi-sophisticated region. So the nice thing here, right? So this looks fairly complicated. If you're trying to do this as a line integral, you would fail. Well, you wouldn't fail, but it'd be a very, very difficult line integral. We have an exponential to some high power, and we have some cos y squared in here. So the thing you have to realize is that invoking Greens theorem in this case gets rid of all the basket of undesirable functions in here, right? Because we're going to take this and take the derivative with respect to y, right? So this disappears. We're going to take this component here and take it the derivative with respect to x. So this disappears. All right, so something that is seemingly very complicated after applying Green's theorem becomes extremely simple, right? Provided that you're able to find the region that's enclosed by D. So after that, we have this, and we just work through it. It's very routine, and you get a third. Right, so Green's theorem is very useful, but it takes practice, right? Because you have to sort of start noticing these patterns from within the examples. I know on the exam we typically say use Green's theorem. Okay? So for the exam, I want you guys to get really good at being able to convert between these types of forms, right? Between going from a line integral to a double integral over a region, right? I want you to be able to take an integral and apply a transformation to it, right? Like more than half of the integral questions I ask you on the exam don't require integration, right? It's just asking you what the bounds and stuff should be, right? So put most of your focus on sort of the setup of these integrals. As we were spending, like I usually do that very quickly because I assume you're comfortable with doing single variable integration. So on the exam, my section, this vector calculus part, it is the vast emphasis on my half of the exam is, can you perform the integrals that I have taught you, right? And since the only thing I care about is to be able to convert these regions, I don't care that you can do single integration, right? That should be it. So please, I want to be able to give you all high marks. Okay, so next week we're going to do curl and divergence, so I'll see you then. Want a clicky pen?
I'll take one. I'll just keep handing out my hand. Anyone want a free pen?
You pass that along.
I will.
If you'd like, I can send you the source for the notes if you want to learn LaTeX. But it's going to be overwhelming.
I actually found some mistake in the notes.
Cool.
Just people.
If you pass me my iPad, maybe I'll take some notes.
Oh, right.
Maybe do that.
It's the home button now at the moment.
I just got this yesterday.
Yeah.
Okay.
Right down the end, it was on the stuff we were doing like just before the break, and it was really the same thing as you're doing here, isn't it? I have a dy there.
Opposition. smart, I would just put this in my Dropbox or something.
How do you like the big iPad? It's very, very huge, isn't it?
It's very big.
Yeah.
But for, so I wanted it so I could stop having to print out stuff, so I could be like, oh, okay, so like, oh shit,
It's like page 110.
I got a third. This is my other textbook. This is the textbook that is actually, you could buy.
Oh, okay. Oh,
It's not as nice as the new one, though.
the 8th edition? Or your book?
No, my book, Stochastic Processes.
Okay.
Anything, okay, what else?
That was it at the moment.
Cool.
Yeah. Oh, in Notability, as long as you go onto any line, go on the eraser. Yeah, when you got the eraser, as long as you highlight anywhere on the line, it deletes the whole line.
Okay.
So we can just draw stuff. We don't actually have to rub the whole line out. We just
There's other stuff that I thought would work, but okay,
yeah, that only came out in the last update.
it just wasn't working for me now. That's what I was trying to do with these.
That would be really, because I use Notability to do all the web assignments. It'd be really nice.
Well, they have smaller ones which use the pen now.
Yeah. Can you hang on this?
You can? There's a Pro?
No, I think all.
You can't use this pen on there.
Can't you?
No, this is the Apple pen. This is why I have such great, this is why it's so nice and tactile. Well, no, you have to pair it. It won't even work.
Bluetooth?
Yeah, but it won't work with
Yeah,
your thing.
yeah.
This is what distinguishes the Pro from the the Pro from the non-Pro.
Yeah.
Right, is the fact that you can use the
Okay.
pencil.
Okay. I want to service them.
Yeah, I don't really see. I'm just too locked into the Apple ecosystem at this point. I don't have to rebuy everything. Plus, I run a family share for me and my sisters. We all have things. Like I buy the app, and then they all can use it. So.
Yeah, that's excellent. Well, I found the 7th edition of the textbook.
Okay.
I really like the front cover on the 8th edition.
You like the 8th edition?
I like the graphic on the front of the book.
The violin?
Oh, I didn't know what it is.
Oh. When I studied, it was a violin. Yeah, that's a violin.
Yeah.
And like the integral sign. Stuart was actually a very avid violinist.
Yeah, I played violin. When I was small.
You keep it up?
Yeah. Play once a week or so at church.
But yeah, this is the.
I'm not sure what the one he's in. What's the one on WebAssign?
Oh, I don't know.
Because there's a.
I thought they're all variations of this.
Oh, it might be one in color. Oh, this is that one there. It's the same thing.
Yeah, it's all a variation on this side of the violin. Nice guy. There's an army of graduate students who prepared the questions and you can actually find the solution manuals too. There's very comprehensive solution manuals to this to these books.
Same book, or is it
yeah, that's not Stuart. That's the.
Yeah. I think that's that they referred me to when I was looking to read more on Riverside.
Well, for the DE parts of the course, sure.
Okay, it's two different. Sure, of
You
course.
haven't realized that until this point that we're running two different courses
No,
concurrently.
I knew that. I just didn't realise for the text.
Differential equations on right on the front of it.
Because I have